Good afternoon, everyone, or good morning, depends on where you are. Welcome again to the new seminar of the ESO Hypatia Colloquium series, which is a series dedicated to early career scientists. So the speaker of this series are all PhD students, all astronomers or researchers up to third year from the PhD. So they were selected through a very competitive selection process. And we congratulate with all the speakers, and we today again with two excellent and exciting scientists talking about very great science. So we are very, very looking forward to listen to the talks. So I don't want to cut the time, just to say very quickly that the way the event works, participants can make questions using the chat on YouTube if you are attending the talk on YouTube, or you can, if you are attending the talks inside Zoom, then you can make the questions, raise your hand, and then I will, probably you notice that now you joined the meeting and you cannot unmute yourself, but raise your hand, please, and I will unmute you so you can make the question, or alternatively, you can use the chat on YouTube to make also the question if you don't want to talk yourself. But we are very happy if you can do that. As you know, the event is streamed on YouTube. So people who are at the moment on Zoom, they agree that this is streamed on YouTube. So please, if you do not agree with that, please leave the meeting. With that, I would like to also thank the two chairs of today, which are Jakub and Tutku. They are a student and a fellow, a fellow and a PhD student here at ESO, and I would like to thank them as all the fellows and students of ESO that are helping us with chairing the session. Thank you for making this happening and for your help. And with this, I would like to give the word immediately to Jakub that can introduce our speaker today, and then we can start with the event. Thank you very much again, and enjoy the event.
Thank you, Giacomo. Hi, hello, and welcome to everyone. It's my pleasure to have you here at this week's edition of the Hypatia Colloquium. And as Giacomo said, today we'll have two speakers, two talks. The first talk will come from Antoine Dumont from University of Utah. And the second talk will come a little bit later from Geray Karademir, who will be introduced by Tutku. But first, Antoine is going to talk to us about, he will reveal, in fact, the origin of the most luminous globular clusters in Centaurus A galaxy. So I will now stop sharing the screen, and Antoine, you can start sharing your presentation.
Hi, thank you, Jakub, for the introduction. Can you see my screen?
Yeah, we can see it now. It's all good.
Perfect. Well, thank you again for the invitation. And thank you, everybody, that for attending. As I said, Jakub said, I'm going to be talking some of the research I've been doing during my PhD here at the University of Utah, working with Professor Anil Seth. I'm a last year PhD student. And specifically, I will be talking about the origin or the nature of some of the most luminous globular clusters in Centaurus A galaxy, which is this galaxy you can see here in the background. I first want to start by talking about nuclear clusters. Nuclear clusters are very dense, compact, and massive star clusters located at the center of a majority of galaxies. These nuclear clusters are present in galaxies with a variety of morphologies, stellar masses and ages, and an environment too. Observationally, we can detect them by analyzing the surface brightness of profile of the galaxies, and we detect this excess of light in the innermost part of the galaxy. For example, here in the plot in the left, I show you the nuclear clusters of this low mass early type galaxy, NGC 205. And in the lower panel, you can see here this excess of light in the innermost part of the galaxy that we associate with the nuclear cluster. These nuclear clusters in general have sizes of around 10 parsec and stellar masses ranging from 10 to the 5 to 10 to the 8 solar masses. My point here is that given the hierarchical nature of the galaxy formation, we expect low masses to merge into larger ones, and during these mergers, the tidal forces can disrupt the smaller galaxies, The nucleus or cluster, however, is tightly bound to the gravity and can survive these mergers and can be left orbiting the halo of the larger galaxy and looking pretty much as a massive globular cluster would look like. Evidence that this nucleus or cluster can survive the tidal forces during mergers comes in the existence of the ultra-compact dwarf galaxies, or UCDs by short. These UCDs are bright stellar compact objects that with sizes and stellar masses between those of globular clusters and dwarf ellipticals. Here in the left panel, you can see the masses and sizes for globular clusters and dwarf ellipticals and UCDs. There is no clear boundary between UCDs and globular clusters. That means there is no clear distinction in sizes or mass where globular clusters finish and where UCDs start, but usually something of around the size of mass of omega Cen, which is the most massive globular cluster in the Milky Way in our galaxy, is considered a UCD. Surprisingly, though, these UCDs do share the properties similar to those we observe in the nuclei of the galaxies and the nucleus clusters. Here in the plot on the right, for example, you can see this nucleus cluster shown in the orange overlap with the population of those most massive globular clusters, or UCDs, shown in red. This gives us some evidence that some of these UCDs, in fact, may be just the survival nuclei of strip galaxies, and the rest of the UCDs may be just ordinary globular clusters, very massive ordinary globular clusters. So the problem here is to distinguish within the UCD, which one are strip nuclei clusters and which one are just regular globular clusters. Evidence, of course, for the strip nuclear formation scenario will come obviously from tidal features that you could observe around these UCDs, then streams like or any kind of stellar feature around them. So those are very faint, of course, and hard to observe. Another evidence could be, for example, to distinguish them from regular globular cluster, it could be extended star formation history associated with their pre-stripping phase. And one of the most exciting ones, I think, will be the presence of supermassive black holes inside them. We know that supermassive black holes are present in most of the galaxies, and of course, they will be present in the center of these nucleus or clusters. And so if some of these UCDs are strip nuclei, we expect this some of them to host at least supermassive black holes. These supermassive black holes, we don't expect them to exist in just regular globular clusters. So evidence for black holes in UCDs came early from dynamical mass-to-light ratio observations from integrated light in UCDs. Here you can see, for example, the plot in Minsky 2013, where he shows the most massive UCDs in red tend to have higher dynamical mass-to-light ratios compared to local globular clusters. The dynamical mass-to-light ratio, we expect this, he suggests that these high dynamical mass-to-light ratios will be the result of these UCDs having high mass fraction black holes of around 10% of the total UCD mass. And these big massive black holes will raise the dispersion of the stars around them, making us to overestimate the dynamical mass when that we observe through the integrated light measurements. This has been confirmed for the 5 most luminous UCDs that we know. Also, most luminous, of course, they're also more massive. Here, the first one, it was MCD-UCD1 in the Virgo cluster, which is around 16 megaparsecs away. Seth and collaborators use integral field spectra here to create dynamical models of this UCD. And what they found is the dynamical mass-to-light ratio of the outer part of this UCD was consistent, for example, with those of regular globular clusters. And there was a peak, or this increasing of the dynamical mass-to-light ratio at the center of it, that was associated with a supermassive black hole of around 21 million solar masses, which at the same time was making up around 18% of the UCD mass. Unfortunately, this is not possible for lower luminosity systems for instrumentation limitations, and we need to search for UCDs, lower mass UCDs, closer to us. Clear candidate to search for lower mass UCDs, where we could detect potentially dynamical signature from these black holes, is Centaurus A. Centaurus A is the nearest giant elliptical active galactic nuclei to distance of 3.8 megaparsec. Centaurus A is a central galaxy in its group, and there is evidence for a complicated merging history that will produce this strip nuclei that will hide among its UCDs population. So my goal has been basically to search for UCDs or massive globular clusters in this galaxy, in the outer parts of this galaxy, to then determine their dynamical mass-to-the ratio to find evidence for globular clusters that could harbor some massive globular clusters. Collaborators and I created this beautiful catalog for around 40,000 globular clusters in Centaurus A. You can see some of those, how those candidates, some of them looks like here in the plot in the right. Most of them looks like B, where it's just kind of like an extended object in the sky. And we have selected of those 40,000 candidates, we have selected 321 to do spectroscopic follow-ups to confirm them that they belong to Centaurus A. As I said, we carried spectroscopic follow-up between 2017 and 2019 from two different shell spectrographs mounted in the Magellan telescope in Chile, M2FS and MIC, for 321 luminous UC candidates based on those catalogs that I showed you before. Here in the lower panel, you can see three examples of how the spectra looks like for these candidates, shown in black. And our best spectral fit is shown in red. The idea, we obtained spectra in two different bands, in the magnesium triplet, which is around 5,000 Armstrong, and in the calcium triplet, 8,600 Armstrong. As you can see, we can clearly resolve the stellar features, and using the spectral fits, we can determine the rate of velocity, which is a shift of these lines, and also the internal motion of the star, which is the velocity dispersion, which is how what is the width of these lines. For these 321 candidates, we were able to measure the rate of velocity for 161 of them. We have enough signal to noise to measure the rate of velocity for 161 of them. And we clearly can separate globular clusters from foreground scales. In the plot in the left, for example, you can see that the globular clusters falls into this high rate of velocity clump with high also velocity dispersions. Centaurus A has a rate of velocity of around 540 kilometers, and we expect this population of globular clusters to distribute around this velocity. And then we also see we can separate foreground stars that have lower rate of velocities and velocity dispersions very close to our instrumental limit. For those 161 objects that we can measure the rate of velocity, we can identify finally 78 as belonging to Centaurus A, being Centaurus A globular clusters, 27 of them being newly discovered globular clusters. For the 78, at the same time, we can measure the internal motion of the stars, the velocity dispersion, for 57 of them, which are shown here in the plot in the right. As you can see, the velocity dispersion correlates well with the magnitude, the G magnitude, which is kind of what we expect. Brighter globular clusters will have higher masses and will have higher internal motions. And of these 57 velocity dispersions, 48 are new measurements. That means that of these 57, only 9 had previous literature velocity dispersions. As I said, the goal here was to combine kinematic measurements with sizes to determine the rate of the virial mass to constrain the dynamical mass-to-the ratio for these luminous UCDs or UCDs. Unfortunately, for this sample of 57 globular clusters, we only have HST imaging that we could determine their luminosity profile for only 10. And the available ground-based imaging PISIS imaging that I showed you at the beginning does only partially resolve the majority of this cluster. For example, a distance of Centaurus A, a global cluster for 3 parsecs will correspond to 0.16 seconds, where the seeing of this imaging was around 0.65. So instead of using HST imaging images, we have used Gaia photometry as a proxy to determine the sizes of these clusters. We collected a sample of effective radii from HST images for globular clusters in this galaxy, which you can see here in the right. These are literature objects; they're not the same 57 that I was showing you before. And we correlate them with their Gaia G magnitude and also with the VPRP excess factor. This VPRP excess factor is sensitive to extended objects in the sky, as it's a comparison of 2 different apertures in Gaia. This is clearly not the science that Gaia was intended to do, but actually works very well at determining the sizes, and we can recover the sizes for this cluster with an uncertainty of 14%. I think this relationship is quite interesting in the sense that it potentially could be used to determine globular clusters, sizes, or UCDs for other galaxies too, as this only depends on the apparent size in the sky. Anyways, combining those kinematic measurements plus dispersion measurements with their sizes, and also determining the V-band magnitude for these 57 globular clusters or massive globular clusters, we can finally determine the dynamical mass-to-light ratio, which you can see here in the plot in the left, shown in red. We also plot them versus previous measurements for UCDs also in Centaurus A, and also globular clusters in the Milky Way and M31. Interestingly, here we see there is a big outlier, of course, around mass-to-light ratio of 7, which is turned out to be the second most massive globular cluster in Centaurus A, and also the highest dynamical mass-to-light ratio of all the local volume, and with also a very extended size. So it's a very good candidate for a strip galaxy nuclei. What we can see here, maybe in the plot on the left, is that our measurements, dynamical measurements, mass-to-light ratios extend around this plot, but some of them are clearly offset towards high elevated mass-to-light ratio, dynamical mass-to-light ratios compared to normal globular clusters. This can be seen more clearly, maybe if we plot their distribution, shown here in the right. So in blue, light blue, you can see the distribution for the dynamical mass-to-light ratio for those objects in red, compared with globular clusters in M31. What we can see here is there is a clear bimodality distribution, with one population of globular clusters peaking around 1.5, and a second population of globular cluster peaking around 2.6. This bimodality is different from the observed distribution of normal globular clusters that we expect to be in M31. As I told you before, one hypothesis for this bimodality distribution, it will be that the second population of clusters just host central massive black holes that will raise the velocity dispersion and create these elevated dynamical mass-to-light ratios. We can test this hypothesis, and we did by creating spherical genus dynamical models using the mass-to-light ratio of 1.5, as it will be the true mass-to-light ratio for these clusters, and feed these models with a grid of different black hole masses until we are able to reproduce its observed central velocity dispersion or mass-to-light ratio. What our models show us is that we expect black hole masses of around 10%, actually between 4 and 18% of the luminous globular cluster total mass. Could explain this by their elevated dynamical mass-to-light ratios. Here you can see the results plot in the left compared to previous similar works, for example, Minsky, which I showed you in the introduction, and also the black hole masses for those massive UCDs that are in red. This high mass fraction black holes, of course, is evidence for the strip nuclei scenario, as we don't expect these high mass black holes to live in regular ordinary globular clusters. We can also do a consistency check with the black holes to see what it will have been the original nucleus or cluster of the ancient galaxy based on their using scalar relationships between black hole mass, galaxy mass, nucleus or cluster. This is shown here in the right. This is just a rough estimate, but it's still meaningful. Here in the x-axis, you can see the stellar mass for these 20 objects without the black hole versus the y-axis, which will be the predicted nucleus or cluster based on the scaling relationships that I was describing before. We see a surprising good agreement between the predicted nucleus or cluster mass for this object, given the large scatter of these scaling relationships, especially at low stellar mass. So with that, I would like just to start concluding. I show you new high resolution spectroscopic measurements for 321 luminous globular clusters in Centaurus A. Of the 321, we determined 78 to belong into Centaurus A, and 27 of those being new discovered globular clusters. We also present the velocity dispersion for 57 of them, with 48 being new available measurements. These more than double the sample of velocity dispersions of this mass limit, and represents measurements of nearly half of all the luminosities that we estimate to exist around Centaurus A. Using these kinematic measurements combined with size determinations, we are able to determine the dynamical mass-to-light ratio for these 57 massive globular clusters. We found that a bimodality distribution in the dynamical mass-to-light ratios in Centaurus in globular clusters in this galaxy that is different from what we observed in the local group. We also found this. We found the second most massive globular cluster in this galaxy, and which is also the highest dynamical mass-to-light ratio of a cluster in all the local group. And plus its extended size measurement, we put it as one of the best candidates for being the survival strip nucleus or cluster. This bimodality distribution observed in the dynamical mass-to-light ratio suggests that central black holes of around 10% of the total cluster mass could be responsible for the elevated dynamical mass-to-light ratios. And if you want to see more details about this or the research, please go and see the link here or on my personal website. I think with that, I'm finishing right now.
Thanks a lot for this talk. Virtual clapping too. I think it's a very exciting topic and also intriguing hypothesis on the presence of the black holes in these clusters. So with that, I'd like to open the floor to the questions. Now you can ask the questions in the YouTube chat as well as in Zoom for those who are here. I already see the first question in Zoom from M. Hilker. Please,
hello.
Please go ahead.
Yes, here, Michael Hilker here. Thanks a lot. Very interesting topic, of course, for me as well. So you showed this interesting result of the bimodality of the mass-to-light ratio. So elevated mass-to-light ratios can have various explanations, among them also initial mass function. You know this probably from the literature. So have you correlated this also with some other parameters like metallicity? Is there the second peak more metal-rich ones or less metal-rich ones? So that would be interesting to know.
It is. We did search for some type of gradient with a color or a metallicity for this high dynamical mass-to-light ratio population. Unfortunately, we do not only have just light based metallicities based in these fits, so they're not super reliable. Though we did find them actually kind of meaningful, but we didn't see any kind of trend or correlation with color or metallicity.
Okay.
I know that there is some type of metallicity mass correlation for UCDs, also observed from simulations, but I believe that these correlations start getting a little bit more tight for masses beyond 10 to the 7. And these are somehow smaller, so that could be a possibility why we don't see something.
If I have another question, I don't know whether someone else is there.
Go ahead. I think we have.
Yeah. Okay. So, have you estimated for Cen A? You can have simulations. How many stripped nuclei you would expect, more or less? Have you done this exercise? How many dissolved nucleated dwarf galaxies actually you expect? So, are the numbers consistent with the second peak or with your numbers? Or
yeah, that's a very good question, and I haven't done the exercise myself. So I only know what it have been done in the literature in that sense, and we can compare to that. I know there has been estimate of course, this for the most massive ones. This kind of 10 to the 7 mass cut is kind of always very present there, and for those ones, I know there's now newly available kind of hydrodynamical simulations that it counts that mostly all the UCDs above them kind of mass will account for the population of UCD, the strip nucleus will account for all the population of UCDs at that mass, but a lower mass is different. I know that there is a more observational kind of constraint that say maybe 5 to 10% of those UCDs could be strip nuclei between the masses of omega Cent to 10 to the 7. But other simulations, I know Maya's 2021, which is a very recent paper, they were saying that maybe 80% of those of the UCDs could be strip nuclei at this mass range. So we definitely find somehow a fraction that is higher than that 5%. That it could be still consistent somehow, maybe with those hydrodynamical simulations. So,
okay, thanks a lot. Bye.
Thanks for the question. We have more questions in the YouTube chat here. So Marina Reikuba says, thanks for the very nice presentation. Based on the success fraction to spectroscopically confirm GCs, as well as the Gaia selection of GCs, can you comment on the total population of globular clusters in Centaurus A?
Yes, that's a very good question. Thank you. We did that as we have an estimate for the total we expect, what is the population that we expect of globular clusters, and this mass range, list of luminosities brighter than 10 to the 5, and we expect around 140 maybe globular clusters at this mass range.
Thanks a lot. And there's a question from Avinash Chaturvedi in the YouTube chat as well. A very nice talk, Antoine. What kind of spatial distribution of UCDs or globular clusters in general have you observed in Centaurus A?
Yeah, we are analyzing that right now. So I cannot tell you much more, but of course the idea will be to compare it to if the UCD distribution, of course, is somehow different than just what we observed, this bimodality between blue and red globular clusters. That will definitely be very interesting, and we're doing that right now.
There's one more question from Marina, similar to Avinash's question. Is there a correlation between substructures seen in PSCEX surveys and the location of massive globular clusters that could be stripped nuclei?
So, sorry, if I understand well the question, if there's a specific distribution for this more massive globular or this strip nuclei compared to globular clusters? Is that correct?
I think so, yes.
For this galaxy, as far as I'm concerned, I don't know, since still distinguishing between them is part of the process right now. We do I know that simulations maybe expect them to be somehow maybe closer to the center of galaxies than farther out.
Mm-hmm. One thing I was wondering is whether bimodal distributions such as the one that you unveil here, is this something observed in the Milky Way as well?
No, and that's not. It's not because there are no UCDs that will have black holes in their centers per se. It's mostly because there's some type of correlation between the masses of with respect of UCDs with the cluster mass, and for Milky Way or M31 clusters, we expect them to have smaller globular black holes, for those of UCDs in Centaurus A, and they will not be massive enough to see these kind of dynamical signatures of the derivative dynamical mass derivation. So there's potentially there are globular clusters that have black holes, massive black holes. I think there are some good candidates actually, right? But we expect them somehow these black holes to be smaller than in those of the UCDs in Centaurus A. So we don't see this kind of bimolarity distribution.
So would it be possible in the case of these lower mass black holes from potentially strict galaxies to distinguish them from intermediate, to distinguish them from, let's say, intermediate mass black holes that would form in situ in globular clusters? Or
yeah, I mean, globular clusters we expect, since the environment will be quite different if these UCDs are the nuclear star clusters of galaxies, because nuclear star clusters have more gas. Globular clusters would not. So the black holes in the globular cluster, we expect them to just form from stellar mergers or and processes like that, and they produce black hole fractions of around less than 1% of the total mass of the cluster. While for the nuclear star clusters, of course, we can expect these higher fraction masses of 10%, and so on. So they are quite different in that sense, yes, because of their environment they are formed.
Thanks a lot. I think we have a little bit, there is a correction from Marina to her question from before. I think the question was about whether you observed the correlation between substructures in the halo that I presume could be related to past mergers and the GCs that could be stripped nuclei. I think that was the
substructures in the halo. I don't know. I do not know.
So it's a good question then, probably. Yes. Okay, with that, we have to conclude. We have to move on. Thanks a lot for the talk and for the questions, for the discussion, Antoine.
Thank you.
Very interesting.
Thank you.
You can.
I'll stop sharing my screen.
Yeah, you can stop sharing the screen, and I will now give the floor to Tutku, who will share the rest of today. Thanks a lot.
Thank you, Jakob. Hello, everyone. Welcome all. I'm Tutku, and it is my pleasure to welcome Geray Karademir from Swinburne University of Technology, Australia. And his talk title is The Galaxy Luminosity Function via Clustering Based Redshift Inference. Can we find the bottom of the galaxy population? So it sounds very interesting. So I'm going to head to Geray right now. So you can screen share, I guess.
So Tutku, thanks a lot. So let's get screen sharing done. Yeah, so I hope this works now and you can see the presentation by now. So yeah, first of all, thanks a lot for the quick introduction, and a good morning from my side here from Melbourne as well. So yeah, today I'm going to present to you a new technique which I'm going to use to measure the Galaxy Luminosity Function, and by which I'm going to probe deeper by multiple magnitudes than you would be able with conventional methods. And therefore, I'm addressing the question of kind of like, are we able to find the bottom of the galaxy population, maybe using this kind of new approach? Yeah, so first of all, let's head to a very quick general introduction about the topic. So as we kind of like all know, the distance information is kind of like the key for the derivation of almost any physical quantity, and almost all science and astronomy is more or less relying on robust distance measurements. So in general, a redshift can be directly measured from observations when you can detect and identify a high contrast spectroscopic feature. So consequently, robust redshift measurements, they require spectroscopic observations of sources with emission absorption lines at a sufficient resolution. And yeah, these observations are usually quite expensive time-wise and restricted usually to the brighter objects. And it's quite hard to do these for a lot of objects. So it is therefore kind of like infeasible to obtain SPECs for all objects within a large survey. So just for an example, this for the Sloan Digital Sky Survey, which has imaged about 100 million and even more galaxies, only of the order 1% have been followed up spectroscopically. So this is a very, very tiny fraction, to be fair, about the total number of objects we have actually observed. So this kind of problem will increase in the future. So because given the rate at which like modern surveys, like ESO or LSST or SK, they will image the sky, the fraction of objects which we have spectra for will decrease with time because we simply can't follow up all of these objects. So we consequently have to explore alternative techniques in order to obtain distance information. The one approach I'm going to present to you now today is so-called clustering based redshift inference. I will always call this now the so-called cluster Z's from now on. Just makes it a little bit easier. And yeah, so what are these cluster Z's all about? As it's commonly known, galaxies in the universe, they are not homogeneously distributed. Instead, they cluster quite strongly. So how does this look like? If you look at the plot at the bottom of this page, you can see here for one of the gamma regions, just the 3D distribution of the objects. And you have 3 different redshift slices colored in blue, green, and red. And also you can see what we as the observer would kind of like see on the sky. And you can see that each individual redshift slice has a quite very unique fingerprint on the sky at the end. So we're exactly going to use that. We're going to use this fact and we're going to infer a statistical distribution of the distances for an ensemble of astronomical sources. And we simply do that by cross-correlating the observed positions against a reference set of which we know the redshifts for. So this technique itself isn't completely new, so it has been used before, but for example, for lensing studies, but we are now going to aim this technique for more rather new purpose, and that's the determination of the Galaxy Luminosity Function. Okay, so first of all, what do we need to calculate any cluster Z's? We kind of like, basically we need 2 overlapping data sets, more or less. So first of all, we need a reference data set, which is kind of like tracing the large scale structure. And for our study here, we use the data from the gamma survey. So we use the 3 equatorial regions. So each of them is 60 square degrees on the sky, as they kind of like provide us with very dense spectroscopic redshifts, which we simply need. The second data set we need is a target data set. I mean, obviously, this is the data set which which the redshift distribution is or will be calculated for. And here we have chosen to use data from the kilodegree survey, as they provide as well with quite deep and high quality imaging. In the bivariate distribution, you can see here now in the left panel, you have in orange the SPECs sample. These are the gamma objects, which are kind of like complete up to a magnitude of around about 19.8-ish, and in the R band. And you can see what kind of areas they are populating. And you can also see in this total data set there have been some color cuts, which then have been used in order to distinguish between different kind of populations. So there were also galaxies, ambiguous, and also stars defined within the data set. And for our study in the end, for our target data set, we removed the stars from the data set in order to reduce a little bit amount of contamination, even though this technique is not prone to, there's no interference due to stars, let's say, because the different difference between stars and galaxies is quite simple. They cluster differently. So if you look at them in the sky, they don't cluster as galaxies do. They have a completely different pattern, and therefore they don't cross-correlate with our galaxies, with our reference data set, and therefore don't produce any signal within the final cluster Zs. Yeah, so these are the two main data sets. In addition, you also have to calculate a random data set, which is needed to reduce the bias of the reference data. And yeah, as you can also see, in comparison, on the left-hand side, you have the SPECSI sample, where you could go to a magnitude of 19.8. If you take a look at the right one, at the target data set, you more or less, we have chosen to minimize incompleteness issues. So we limited our study to a magnitude of 22.5. So that's giving us, a fair amount of almost 3 additional magnitudes in depth. And yeah, just to give you a little bit of comparison, there's also a few data points overplotted here. These are the UEGs by Van Dalen in 2015. So these kind of objects are definitely included within our analysis as well. Okay, so as we now know what kind of objects or like data sets we need, let's give you a quick illustration about how the clustering redshift process works for the 3 gamma regions. In the left panel, you can see the contours of 3 different redshift slices, again in red, blue, and green, at redshift 0.1, 0.2, and 0.3. And on top of the target dataset or subset of the target dataset in black. And you can see very nicely the, very individual fingerprint, these kind of areas, or like these redshifts produce on the sky. So what we're going to do now, what the classes are doing now, they are more or less calculating the cross correlation between all target data sets, so between all the black points with the different reference points at each redshift. And we kind of like get a cross correlation function, which is dependent on an angular distance, or if you on a physical distance if you transform it. In addition, also the autocorrelation function is calculated between the reference set and the randoms, which are not shown right now because they are homogeneous, so you wouldn't see that much. And yeah, which is then needed to reduce the reference bias. These kind of functions you can see in the middle. So, and by integrating these within a certain clustering range, you are then in the end able to get the final P of Z, or the final cluster Zs. You can see them here on the right panel. You can see the data points, amplitudes this routine kind of like produces for the different slices. And you can also see that one measurement itself in that sense is not providing that much information. But if you do that really for a lot of different redshift slices, you can see how you in the end get the P of Z of your target set. So you get the redshift distribution of the data set you didn't know before. The one thing I want to highlight here is that during this whole process, the only information required of the target data set is more or less just the position on the sky. So we're not using any more information. It's just the observation itself. And this is sufficient to get a redshift distribution from. So in order to get the luminosity function, we also not only need the redshift information, but we also need some magnitude information. So what we do is that we split up the unknown data set by magnitude into different subsamples, and we simply redo the analysis for these subsets. So in the end, we obtain a 2D grid, which is shown here. What you can see here is more or less that it's not showing the anticipated shape of the galaxy distribution as we would have expected. The reason for this is that the output of the cluster Zs, unfortunately, is only proportional to the true number distribution, and therefore we need some sort of normalization. Also, unfortunately, a simple direct normalization is kind of impossible, because the easiest approach would be just to normalize the resulting function so that the integral is equal to the number of objects within that magnitude bin, for example. But unfortunately, that's not working. So the reasons for this is, so firstly, we simply don't know. We can't guarantee that all objects are galaxies, and therefore, contamination by stars, for example, would change our normalization quite significantly, while stars are on the one hand side here not producing any signal in the clusters, but they will mess up the normalization. So this kind of problem we kind of like would be able to solve if we just inspect our data very carefully. But there's an even more severe reason why this is not possible. Because the second reason is quite simple and straightforward. We simply don't know if all the objects we have within our target data set, which in our subset, are within the redshift range of our reference set. So objects which are beyond that, obviously, are not producing any signal. But on the other hand side, they would, would take some part in the normalization. So our clusters can be incomplete in a sense in terms of redshift, because we of course can only trace the redshift distribution as far as our reference set goes. So this kind of very simple normalization attempt unfortunately simply won't work, and we need to come up with something more flexible. So what are we going to do now? So we have defined a new normalization factor. We call it the so-called the A factor, and we just defined this factor to be the one which transforms clusters to number distribution n of z and vice versa. So what is the A factor now? A factor can be derived analytically quite simple from simple chi-squared analysis, and it's working in a way that it's simply comparing the clusters within a certain magnitude bin with a given number distribution and just finding the best fitting normalization. So it's only changing the amplitude, but not the shape of the redshift distribution. That's something I would like to highlight here. So this also kind of like gives us the opportunity, of course, to define some sort of likelihood estimator, which we're going to need later on in the fitting process for the luminosity function. But first of all, let's have a look if this kind of normalization process works. So here in this panel, you can see how the resulting clusters in each equatorial field at multiple magnitudes here in blue. And in addition, the A factor normalized gamma spec C redshift distribution is overplotted here with these orange bars. And what you can see that the resulting clusters very well in agreement with the true redshift distribution here. So the clusters are truly giving us a very, very good estimate of the true redshift distribution. There's only one main bias, which this kind of method is dealing with, and you can see it here already very clearly. So that's the differential bias evolution of the unknown data set, of the target data set. We have accounted for the bias of the reference set, but to account for the differential bias of the unknown set, it's much, much harder because we simply don't know that much about this data set. So this kind of bias usually leads to an overestimation of the clusters at higher redshifts, and you can see it here quite nicely in a few of these bins. And that's also one of the reasons why we have chosen to focus on the low Z Galaxy Luminosity function in our results, just to minimize the effect of this bias. Okay, so quick thing about the Galaxy Luminosity function. So why are we looking at it? Our plan or our study is focusing on the faint end slope of the Galaxy Luminosity function. And the faint end slope is quite crucially, it's important in order to constrain structure formation theories, because at low luminosities, theoretical models and simulations and observations are very difficult and sometimes very different. And this is just due to multiple reasons. So just obtaining a robust measurements in the field, so getting robust measurements of the cosmic average Galaxy luminosity function at very low luminosities, it remains an observational challenge. And because it simply needs very deep data to probe the faintest luminosities, but you also need quite large areas because you have to get significant volumes at low redshifts. And this is still an observational challenge, and it's quite time consuming. So what we're going to do now, we are aiming to expand the galaxy measurement beyond the limits of the spec C. So currently that would be the 19.8 magnitudes. And trying to find the bottom of the galaxy population, because you could, in general, you could ask yourself, as the total number of galaxies, it's a basic observable quantity, it should be countable and finite. So there should be an end to the Galaxy Luminosity Function in some sense at some point. Yeah, so no Galaxy Luminosity Function goes without any kind of formalism and kind of modeling. So we have chosen to use a double checked function for our model with a simple evolution model as well. And here I just want to notice that the slope parameter here is kept constant while the other parameters are allowed to evolve with redshift. And the other thing which is very important to mention here is, as I mentioned the A factor normalization before, it is essentially modifying the amplitude of the cluster Z's, which in the end means that it's modifying the density of our cluster Z's at each magnitude. And this results in a degeneracy with the density of the model itself. So just fitting to the cluster Z's won't give you any information about the densities of the Galaxy Luminosity Function. So in order to break this degeneracy, we will use the species, and we are going to constrain it by adding a second likelihood term. And in general, it would be possible to just use some finite values from the literature. So that's also one thing you can do. But on the other hand side, as we have this kind of reference data set, which we used before, we're just going to use it again to define phi naught. These two likelihoods functions then will get maximized using MCMC, and yeah, we get some nice results. So yeah, let's have a look at it. Here, I'm going to show you a quick an overview how this kind of process now finally works. So on the left, you see as before the unnormalized cluster Z's. So what happens after the fit and after comparing them, normalizing them correspondingly to the best model, that's what happens when you can see here in the middle panel. And you can see how the galaxy population more or less just pops out of nowhere, and how this is a really nice way of getting these results. And in addition, if you then add the distance modulus, you can literally see the kind of full extent of our study here now on the last panel on the right. But now let's get a little bit more into detail. Yeah, let's have a look at first at the resulting source counts. The solid points are the gamma or bikings, the data binned in by magnitude. The calculated models are shown in solid lines and are compared with the A factor normalized cluster Z, so the lines with the arrow bars. And these are shown for the complete population in black, and also for a series of redshift slices here with the rainbow colors. You can see very nicely how the galaxy population is built up, and also how well it agrees with the gamma species where available. And this is a very, very nice first test. The other thing you can also see more or less quite immediately is the kind of drop off you have at magnitudes higher than 19.8, so beyond the completeness limit of the gamma sample. And this decrease simply comes from our incomplete cluster Z's at fainter magnitudes, because a significant fraction of the objects are beyond the redshift range of the gamma catalog, and are therefore our cluster Z's are simply incomplete in terms of redshift. Good. So yeah, by combining the different redshift slices I've showed you just a second before, up to a redshift 0.1, we can now collectively build the Galaxy Luminosity Function, and the result is shown here. So the total extent of the Galaxy Luminosity Function we derived covers over more than 14 magnitudes, or like 5.5 decades in luminosity. And it provides us with more three additional magnitudes information compared to the species themselves. And yeah, the shape itself is very, very common in a sense. So we have the beautiful Schechter-Nein at the very bright end, and then the luminosity function remains remarkably flat between absolute magnitude of -20 to, let's say, -13. But then we see a quite sharp upturn in the end. So here at the faint end, we have quite strong indications that the slope is becoming even steeper. And also, what you always have to keep in mind is that due to surface brightness limitations, our results have always to be seen as lower limits, which is another reason why we're going to conclude that the Galaxy Luminosity Function remains divergent, which you can see here very nicely. So yeah, how does this compare now to the literature? And maybe we can get some more information about this sharp upturn at the faint end. Yeah, so here I'm going to show you now a comparison between the data luminosity data we derived from our study with the literature I've shown you before as well. So first of all, you can see that our result, is in quite good agreement with earlier studies, and also that you can get a lot of additional depth is achieved compared to these studies. And interestingly, a similar upturn has been found for the Coma cluster by Yamano et al. In 2012. And they suggested that globular cluster population is the reason for that. So we just followed Yamano et al. And we used a simple model to predict the luminosity function for the globular cluster population based on our galaxy luminosity function fits. So we assumed we have a galaxy population, which is described by our galaxy luminosity function, and then just derived what number of globular clusters would be based on this population. And what you can see here as a dashed line now, that's the globular cluster luminosity function. And this provides very nice agreement with our global, our total results from the cluster Z's. And this simple prediction, and it's a really simple one, it has no free parameters. And so that's one point where I think it's very amazing that this kind of gives a quite nice indication that we can conclude due to that we have found the end of the galaxy luminosity function, because at this faint end, at these magnitudes, it looks like that globular clusters are taking over to be the main population available, and it's not galaxies anymore. So yeah, let's wrap this up. I've shown you a new experimental design to measure the galaxy luminosity function, and it only considers positions and magnitude. And in addition, we have mapped the galaxy luminosity function across 14 magnitudes, all the way down to where subgalactic objects like globular clusters or maybe ultra-compact dwarfs take over as the most numerous extragalactic populations. This technique itself is very, very flexible, and it offers manifold applications. So it's definitely not limited to the optical only. And therefore, I would like to conclude with a quick preview. So I'm working on right now and trying to derive the bright end in the infrared using 7,000 square degrees on the sky and the data from the WISE satellite. And yeah, so stay tuned and let's see how the result will look like. So thank you very much for your attention, and I will finish now. Thanks.
Well, thank you very much, Geray. That was very interesting. So I guess we can continue with the questions. So if you have any questions from the Zoom session, you can raise your hands, or you can use the YouTube channel to ask your questions. I think Giacomo has a question.
Yeah, Tuktu, thank you very much. Thank you, Geray, for the talk. Sorry, this is not my field, so I apologize for the possible. But so my question is, isn't it basically the way you derive the clustering redshift, basically the way you derive it, that is not very much dependent on the comparison, basically not the group that you use for comparison. So the normalization, the target sample, in a sense, that you use at the beginning that you use to guide basically your clustering.
Okay, so I think you're referring to the reference set now, the one.
Yes, exactly, indeed.
Yeah, okay. Yeah. So the normalization itself is not related to the reference set at all. So that's mainly a thing of the target data set, of the unknown data. The reference set is just very important you have to have a certain density of objects, to trace all the, large scale structure there, because if you're missing a lot of objects, then your resolution just drops quite significantly. So that's the kind of point. I hope I've answered your question.
Yes. And so do you foresee a way to improve in that direction by, having deeper spectroscopic survey, for example?
Yeah. So there are multiple ways of doing so, because the reference set doesn't have to be just one data set. So what I'm currently working on for WISE, for example, here, it's I'm combining SDSS and BOSS, and also I'm also currently trying to include the quasar sample as well. Of course, you have some mismatches between the different sets, but that's working very, very nicely in general. So yeah, you can more or less just add things which are overlapping on the star.
And sorry to have an last curiosity. Maybe it's very just a curiosity. Do you also think that at some stage there is any, so given the experiments that you have been designing, any help can come from machine learning techniques?
Difficult. I mean, the nice thing about it is it's more or less an analytic thing. So yeah. It's so the calculation is analytic. So there's only, let's say, one true answer, which is of course a very, very nice thing. Of course, it would be very interesting. Machine learning would be very interesting in order to maybe get some more information about the unknown biases. So if maybe it's possible to use a way there to get more information about the what's going on there. But I'm not so sure about it. But I'm not having that much experience in machine learning. So yeah, but would be really interested in if someone who knows more about it, yeah, to have a chat at some point.
Okay, great. Thank you very much again.
Jakob?
Yeah, hey, thanks for the nice talk. I was wondering, again, it's not my field, but I was wondering if there is any danger in combining samples from different redshifts to construct a single function, or is that at the redshift similar enough?
What do you mean by combining different sets of different redshifts? Sorry, I think I didn't got your question.
To go to your Galaxy Luminosity Function at the end, the way I understood is that you combine your samples from different bins of redshift, correct?
Yeah, that's what you mean, yeah.
And if there is, so I was just wondering if there is any danger if the Galaxy Luminosity Function is evolving with redshift. It's unknown that, yeah.
And so, first of all, we have evolution included into the analysis to a certain degree, so that should be taken care of. And secondly, of course, if there would be a really strong evolution within a redshift of up to 0.1, which is still very, very close, of course, then it would kind of like, and if we didn't got that right, that's the even more important thing. Then of course it kind of like messes up. The only thing is just every kind of Galaxy Luminosity Function is more or less based on different redshift slices, because each galaxy is at a different redshift. The only difference is just, you have it usually on a point-based thing. Well, I unfortunately, due to the process, are limited to a binned approach. So I'm not having this kind of, that much amount of information, unfortunately. That's the reason why it might look a little bit differently. But yeah. But even if you're not fitting for the evolution at all, the result doesn't change that much at these redshifts. So,
right. Yeah.
Of course, if you go to higher redshift, then things will change. But that's a really low redshift Galaxy Luminosity Function. So there, everything should be fine.
Okay, thanks.
Any other questions for Geray? We don't have any questions on the YouTube channel, but yeah, I guess I'll hand to Giacomo for closing.
Yes. Okay. Thank you, Tuktu. Thank you very much for Tuktu and Jakob for chairing the session, and thank you for the Geray and Antoine for the nice talks, for the great talks. Congratulations and good luck for your career. And of course, let me remind everyone the talks will stay online on YouTube, on the YouTube. There is a playlist that you can watch, where you can watch these and all other talks of the series. And the next one won't be, so we see again in 2 weeks, as next week there will be a conference on astronomy and the present and future of astronomy. There is a lot of people subscribed, so we are looking forward to this new event that takes place next week. Is a kind of series of duologues, of cosmic duologues, and we happen next week. So next week we focus on that, and then we come back in 2 weeks. So we can close. And thank you very much again. Thank you for people for coming and for staying with us and for making questions. And see you in 2 weeks. Thank you very much.